Tonight, we're going to confront something that should be impossible. The most successful theory of gravity ever conceived. A theory that has passed every experimental test for over a century. A theory that predicted phenomena decades before we had the technology to detect them, produces an answer that destroys itself. Gravity. You feel it right now, pressing you into your chair, holding you to the surface of the Earth, keeping the moon in orbit, binding galaxies together across millions of light years. It is the most familiar force in the universe, and yet, when you follow Einstein's own equations deep enough, past the event horizon of a black hole or back to the very first instant of the universe, they don't just stop working, they produce infinities. Physical quantities that blow up to meaningless values. The most rigorously tested description of gravity ever written contains the seeds of its own destruction. And after more than a century, no one knows how to fix it. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, let's begin. You feel gravity right now. You do not have to think about it. You do not have to do anything to make it work. It is simply there, pressing you into whatever surface you are sitting or lying on, pulling you toward the center of the Earth with a force so constant, so steady, so utterly reliable that most of the time you forget it exists. Your coffee settles to the bottom of the mug. Rain falls from clouds. Rivers flow downhill toward the sea. The moon traces its silent arc around the Earth, and the Earth traces its much larger arc around the sun. These things happen every moment of every day, and they have happened for billions of years before any human being was alive to notice them. Gravity is the most familiar force in the universe. It is the first force you ever encountered. The moment you were born, gravity was already pulling you down. When you learned to walk as a toddler, gravity was the thing you had to overcome with every single step. When you tripped and fell, gravity was the thing that brought you to the ground. You have spent your entire life negotiating with gravity, compensating for it, pushing against it, working with it. And you have done this so continuously and so automatically that you barely register it happening. It is as constant as breathing. It is as ordinary as daylight. And for most of human history, no one thought it needed much of an explanation. Things fall. That is what heavy things do. Rocks fall, water falls, people fall if they step off a cliff. The ancient Greeks, particularly Aristotle, believed objects fell because they were seeking their natural place in the cosmos. Earth and water, being heavy elements, belonged at the center of everything. Fire and air, being light, rose upward because they belonged above. It was a tidy system. It matched everyday observation. It had an elegant philosophical logic, and it was almost entirely wrong. Aristotle also taught that heavier objects fall faster than lighter ones. This seems intuitive. If you hold a bowling ball in one hand and a feather in the other and drop them at the same time, the bowling ball crashes to the ground while the feather drifts lazily downward. So heavier things must fall faster, right? Wrong. The feather falls slowly because air resistance pushes against its large surface area relative to its tiny weight. Remove the air, and something remarkable happens. In a vacuum, where there is no air at all, a bowling ball and a feather drop from the same height, hit the ground at precisely the same instant. Apollo 15 astronaut David Scott demonstrated this on the surface of the moon in 1971, standing in the lunar vacuum and dropping a geological hammer and a falcon feather side by side. They landed together, perfectly synchronized, on live television. Aristotle's intuition, trusted for nearly 2,000 years, was wrong. Galileo Galilei had already established this principle earlier, beginning around the turn of the 17th century. He carefully measured how objects accelerate as they roll down inclined planes, and he discovered something remarkable. All objects, regardless of their weight, accelerate at the same rate under gravity when air resistance is removed. Near the surface of the Earth, that rate is about 9.8 meters per second squared. Every second an object falls, its speed increases by roughly 9.8 meters per second. After 1 second of free fall, an object is moving at 9.8 meters per second. After 2 seconds, 19.6. After 3, 29.4. It does not matter whether the falling object is a cannonball or a marble, a gold bar or a wooden block. Gravity accelerates them all identically. The mass makes no difference whatsoever. This was an extraordinary discovery. It was also deeply strange. Why should gravity treat all masses the same? No other force behaves this way. If you push a shopping cart and a fully loaded truck with the same force, the cart accelerates much faster because it has less mass. Force and mass are always tangled together in every other physical interaction, but gravity somehow ignores the difference. A feather and a hammer fall at the same rate. A pebble and a boulder accelerate identically. Galileo documented this fact with painstaking care, but he could not explain why it happened. That mystery would wait more than 300 years for an answer, and the answer, when it finally came, would arrive from Albert Einstein. But before Einstein, the world needed Isaac Newton. Newton was born on Christmas Day in 1642, in the small English village of Woolsthorpe. By his mid-20s, he had already invented calculus, demonstrated that white light is composed of a spectrum of colours, and begun formulating the theory of gravitation that would define physics for the next 2 centuries. The famous story is that Newton was sitting beneath an apple tree when a falling apple prompted him to wonder whether the same force pulling the apple toward the ground might also be the force holding the moon in its orbit around the Earth. Whether the apple story is literally true has been debated by historians for centuries. But the question Newton asked is not debated at all, and it was a question of breathtaking ambition. Could the same force that causes an apple to fall from a branch also reach across 240,000 miles of empty space and keep the moon locked in its path around the Earth? Newton's answer was yes. And not just yes for the apple and the moon. Newton proposed something far more sweeping. He argued that every single object with mass in the entire universe attracts every other object with mass. Every atom pulls on every other atom. Your body is gravitationally attracted to the chair you're sitting in right now. The chair is attracted to the walls of the room. The walls are attracted to the Earth beneath them. The Earth pulls on the moon, and the moon pulls back on the Earth. Both pull on the sun, and the sun pulls on both of them. The sun pulls on every other star in the galaxy, and they all pull back. Gravity is not something that only happens between planets and stars. It happens between everything, everywhere, at all times. It is universal. This was Newton's great insight, and it is why we call his framework universal gravitation. But Newton didn't stop at a philosophical statement. He gave gravity a precise mathematical form. The gravitational force between any two objects depends on two things. First, it depends on how massive both objects are. The more massive the objects, the stronger the pull between them. Double the mass of one object, and the gravitational force doubles. Double the mass of both objects, and the force quadruples. Mass creates gravity, and more mass creates more gravity. Second, the force depends on distance. Specifically, it depends on the square of the distance between the two objects. This is called the inverse square law, and it is one of the most important relationships in all of physics. If you double the distance between two objects, the gravitational force between them drops to 1/4 of what it was. If you triple the distance, it drops to 1/9. If you move 10 times farther away, the force drops to 1/100th. Gravity weakens rapidly with distance, but it never reaches zero. No matter how far apart two objects are, the gravitational pull between them is still there, just vanishingly small at enormous separations. There is an elegant geometric reason for this. Imagine a light bulb radiating light equally in all directions. Close to the bulb, the light is intense and concentrated. But as you move farther away, the same amount of light has to spread across the surface of an ever larger imaginary sphere surrounding the bulb. Double the distance, and the sphere's surface area is 4 times larger, so the light at any point on that sphere is 4 times dimmer. Triple the distance, 9 times dimmer. The light has not vanished. It has simply been diluted by spreading across more space. Gravity works the same way. It radiates outward from a mass in all directions, and as it spreads across larger volumes of space, its influence weakens with the square of the distance. This single mathematical relationship governs the motion of everything from falling apples to orbiting galaxies. Newton published his theory in 1687 in a work titled The Principia, widely regarded as one of the most important scientific texts ever written, and his theory worked with spectacular precision. It explained why planets orbit the sun in ellipses, confirming what Johannes Kepler had described empirically decades earlier, but could not explain mechanically. It explained why the moon orbits the Earth, and why the Earth does not fly off into space. It explained the ocean tides, showing that the gravitational pull of both the moon and the sun on Earth's oceans creates the rhythmic rise and fall of water levels that coastal communities observe every day. It explained why objects weigh slightly less at the top of a tall mountain than they do at sea level, because the mountaintop is farther from the center of the Earth by a small but measurable amount. It explained the trajectories of comets, showing they follow the same gravitational laws as planets, but in highly elongated orbits that carry them far from the sun and then sweep them back inward at tremendous speeds. One of the most dramatic early triumphs of Newton's theory involved Halley's comet. Edmund Halley, a friend and contemporary of Newton, used Newton's gravitational equations to analyze the recorded orbits of several bright comets that had appeared throughout history. He noticed that comets observed in 1531, 1607, and 1682 had remarkably similar orbital characteristics. Halley proposed they were the same comet, returning on a roughly 76-year cycle. He predicted it would appear again around 1758. Halley died in 1742, 16 years before the predicted return. But on Christmas night of 1758, the comet appeared in the sky exactly as Halley had calculated, using nothing but Newton's mathematics. A man had used gravitational equations to predict the future position of a celestial object, and the universe confirmed he was right. The comet was named in his honor, but the greatest triumph of Newtonian gravity came more than a century and a half after the Principia was published. By the early 1800s, astronomers had been carefully tracking the orbit of Uranus, which had been discovered in 1781 by William Herschel, and they noticed something troubling. Uranus was not following the path Newton's equations predicted. It was drifting, arriving at certain points in its orbit, slightly earlier or later than the calculations said it should. The discrepancies were small but persistent, and they grew more pronounced as the decades passed. Something was pulling on Uranus, disturbing its orbit gravitationally, and no known body could account for the disturbance. Two mathematicians, working independently and unaware of each other's efforts, proposed the same breathtaking solution. The Frenchman Urbain Le Verrier and the Englishman John Couch Adams both calculated that an unknown planet must exist beyond the orbit of Uranus, and that the gravitational pull of this unseen world was responsible for the orbital anomalies. Le Verrier went further. Using Newton's equations, he calculated not just that the planet existed, but precisely where in the sky it should be at that very moment. He sent his prediction by letter to Johann Gottfried Galle at the Berlin Observatory. On September 23rd, 1846, Galle pointed his telescope to the exact coordinates Le Verrier had specified. Neptune was there, sitting within 1 degree of the predicted position. A planet had been discovered not by scanning the sky and stumbling upon it, but by pure mathematics. Newton's equations had revealed a world no human eye had ever seen. Using nothing but the gravitational fingerprint it had left on the orbit of its neighbor. It was arguably the greatest triumph of mathematical physics up to that point in history, and it seemed to prove beyond any doubt that Newton had solved gravity once and for all. For over 200 years after the Principia, Newtonian gravity appeared to be perfect. Every observation, every measurement, every prediction confirmed it. Engineers used it to build bridges and calculate the arcs of cannonballs. Astronomers used it to predict eclipses decades in advance. The mathematics was clean, the predictions were precise, and the universe seemed to obey Newton's equations without exception. Gravity had been solved. Newton had written the final word, but there was a problem, and it had been hiding in plain sight. Mercury, the smallest planet and the closest to the Sun, has an orbit that does something Newton's equations cannot fully explain. Like all planets, Mercury travels around the Sun in an ellipse, but that ellipse does not remain fixed in space. It rotates very slowly, a phenomenon called orbital precession. The point in Mercury's orbit where it comes closest to the Sun shifts slightly with each revolution, tracing a slow rosette pattern over centuries. Most of this precession is perfectly explained by Newton's theory. The gravitational pulls of Venus, Jupiter, and the other planets tug on Mercury as it orbits, and their combined influence accounts for the vast majority of the observed drift. But not all of it. After accounting for every known gravitational influence, every planet, every asteroid, every conceivable source of gravitational perturbation, there remained a small unexplained residual. Mercury's orbit was precessing by an extra 43 arcseconds per century beyond what Newton's equations could predict. An arcsecond is 1/3600th of a degree. 43 arcseconds is an almost absurdly tiny angular shift. If you held a coin at arm's length, 1 arcsecond would be roughly the angular width of that coin, seen from about 4 kilometers away. We're talking about 43 of those minuscule increments, accumulating over the course of an entire century. It sounds like nothing. It is almost nothing, but it was real. It was consistent across every measurement. And with better instruments, the discrepancy did not shrink. It grew more certain. Leverrier, the same man who had triumphed with Neptune, proposed a familiar solution. Perhaps there was another undiscovered planet, even closer to the Sun than Mercury, whose gravitational pull was responsible for the anomalous precession. He even gave this hypothetical world a name: Vulcan. Astronomers searched for Vulcan for decades. Some claim to have glimpsed it during total solar eclipses, when the sun's blinding glare is blocked, and faint objects near the sun might become visible. But no confirmed observation ever held up under scrutiny. Other astronomers pointed telescopes at the predicted positions and saw nothing. Vulcan did not exist. The elegant trick that had worked so beautifully for Neptune, postulating an unseen mass to explain gravitational anomalies, simply did not work for Mercury. The discrepancy remained unexplained, stubbornly resisting every attempt to resolve it within Newton's framework. Something else was happening. Something the mathematics of universal gravitation could not accommodate. And Mercury's orbit was not the only problem. There was a deeper, more conceptual difficulty lurking at the very heart of Newton's theory. One that Newton himself was profoundly uncomfortable with. In Newton's framework, gravity acts instantaneously across any distance. When the sun pulls on the Earth, that pull is transmitted across about 150 million kilometers of empty space with no delay whatsoever. There is no travel time, no signal, no propagation. The force simply exists between the two bodies the instant they exist. If the sun were to suddenly vanish right now, in Newton's theory, the Earth would immediately fly off in a straight line. Not after 8 minutes, not after any delay, immediately. The gravitational link between the sun and the Earth would sever at the exact instant the sun disappeared, even though nothing had traveled between them to carry that information. Think about how strange that is. The sun is 150 million kilometers away. Light, the fastest thing in the universe, needs over 8 minutes to cross that distance. Yet Newton's gravity somehow communicates instantaneously, faster than light, faster than anything, with no mechanism, no medium, no carrier. The Earth just knows somehow that the sun is there. And if the sun vanishes, the Earth knows that too. Immediately. Newton called this action at a distance, and he hated it. In a letter written in 1693 to the scholar Richard Bentley, Newton stated that the idea of gravity acting through empty space without any intervening medium was so great an absurdity that he believed no person who had a competent faculty of thinking could ever fall into it. Newton was essentially admitting that his own theory contained something he found philosophically unacceptable. He could not explain how gravity reached across empty space. He could not identify what carried the force. He could not describe any physical mechanism connecting two masses separated by a void. He had written the mathematics, and the mathematics worked. The predictions were astonishingly accurate, but the how of gravity, the underlying mechanism, was completely absent from his theory. This distinction matters enormously. Describing what something does is not the same as understanding what it is. Newton could tell you exactly how a planet moves under gravity. He could predict its position years into the future with extraordinary accuracy, but he could not tell you why the planet moves that way. He could not tell you what reaches across 150 million kilometers of emptiness and pulls on it. He could not explain how a force acts where there is no contact, no material connection, nothing at all between the two interacting bodies. He had written the operating manual for gravity without having any understanding of the engine. And by the late 1800s, the speed problem had become even more pressing. James Clerk Maxwell had unified electricity and magnetism into a single framework and demonstrated that electromagnetic waves, including light, travel at a finite speed of about 300,000 kilometers per second. This raised an unavoidable question. If light has a speed limit, does gravity? If the sun vanished, would the Earth keep orbiting for 8 minutes? The time light would take to cross the gap before the gravitational signal of the sun's disappearance arrived? If gravity propagates at a finite speed, then Newton's instantaneous framework must be wrong, or at least incomplete. But no one knew how to modify the equations without destroying everything that works so well. The mathematics of universal gravitation was exquisitely precise for the motions it described. Any change risked breaking the predictions that 2 centuries of observation had confirmed. These were the cracks, small, almost invisible, a 43 arc-second discrepancy in the orbit of one small planet, a philosophically troubling reliance on instantaneous action at a distance with no mechanism, a complete silence about what gravity actually is at a physical level. For over 200 years, Newton's framework had been the unchallenged foundation of physics. It had predicted the existence of unknown planets. It had explained the motions of everything from cannonballs to comets. It was the most successful scientific theory the world had ever known, and almost every working scientist on Earth considered it settled. But it was not settled. It was incomplete. Not wrong, exactly, because his predictions matched observation with remarkable accuracy across an enormous range of situations. Bridges built using Newtonian gravity still stand. Spacecraft trajectories calculated with his equations still reach their targets. For the vast majority of purposes, Newtonian gravity works beautifully. But at its edges, in the most extreme environments, in the conceptual foundations beneath the mathematics, there were questions Newton could not answer and problems his framework could not solve. Those questions have been quietly ignored or set aside for 2 centuries, treated as minor embarrassments rather than fundamental flaws. They were about to be confronted by a man working in a Swiss patent office, a man willing to ask a question so deceptively simple it sounded almost childish. If a person falls freely under gravity, with no floor beneath them and no wind in their face, do they feel any force at all? The answer to that one quiet question would demolish the entire idea of gravity as a force pulling objects through space and replace it with something far stranger, far more beautiful, and ultimately far more troubling than Newton or anyone else had ever imagined. Not a force, not a pull, but the shape of the universe itself. In 1907, Albert Einstein was sitting in his chair at the patent office in Bern, Switzerland, when a thought entered his mind that he would later call the happiest thought of his life. It was not a complicated thought. It was not a mathematical breakthrough. It was a simple observation about what happens when a person falls. If a person falls freely, if they step off the edge of a building or a cliff or a bridge and plummet toward the ground with nothing beneath them and no wind resistance against their body, they feel weightless. They do not feel gravity pulling them down. They feel nothing at all. Their stomach floats. Their arms drift. If they released a ball from their hand mid-fall, the ball would not drop away from them. It would hover right there beside them, falling at the same rate, because gravity accelerates all objects identically regardless of mass. Galileo Galilei had established that fact 3 centuries earlier, but Einstein saw something in it that Galileo had not. He saw that freefall does not merely reduce the sensation of gravity, it eliminates it entirely. Think about what that means. You are falling toward the Earth. Gravity is supposedly pulling you down with tremendous force, and yet you feel absolutely nothing. No pull, no push, no force of any kind acting on your body. If you closed your eyes and could somehow ignore the air rushing past you, you would have no way of knowing you were falling at all. You would feel exactly the same as if you were floating in deep space, millions of kilometers from any planet or star, in a region where gravity is negligible. The experience of freefall is identical to the experience of zero gravity. Not similar. Identical. No experiment you could perform inside a sealed falling elevator, no measurement, no observation of any kind could tell you whether you were plummeting toward the Earth or drifting through empty space. The two situations are physically indistinguishable from the inside. This is the equivalence principle, and it is the foundation upon which Einstein built the most successful theory of gravity ever conceived. But before we see what he built, we need to understand the full depth of this idea. Because the equivalence principle does not just work in one direction, it works in both. Imagine you wake up inside a sealed box with no windows. You feel your feet pressing against the floor. You feel weight. If you hold out a ball and release it, the ball falls to the floor. If you pour water from a glass, it streams downward in a smooth arc. Everything behaves exactly as it would in a room on Earth. You might naturally conclude that you are on Earth, or at least on some planet with gravity, but Einstein pointed out that there is another possibility you cannot rule out. You might be in deep space, far from any planet, far from any star, far from any source of gravity whatsoever, but your box is being accelerated upward by a rocket engine bolted to the bottom. The rocket pushes the floor up into your feet, which is why you feel weight. When you release the ball, the floor rushes up to meet it while the ball stays behind. And from your perspective inside the box, the ball appears to fall. The water pours downward because the box is accelerating upward. Everything inside the box behaves exactly as if you were standing on the surface of a planet. And here is the critical point. There is no experiment you can perform inside that sealed box to determine which situation you are in. You cannot tell whether you are in a gravitational field or being accelerated by a rocket. Not because you lack the right instruments, not because the differences are too subtle to measure, but because there is no difference. The two situations are physically, fundamentally, completely equivalent. That is what the equivalence principle states. Gravitational acceleration and inertial acceleration are the same thing. Most people hear this and think it is a neat observation, perhaps a curiosity, perhaps a thought experiment with no practical consequence. But Einstein realized it was a clue of extraordinary power. Because if gravity and acceleration are truly indistinguishable, if no experiment can tell them apart, then gravity cannot be a separate force. If the experience of standing on the surface of the Earth is identical to the experience of being accelerated through empty space by a rocket, then whatever you feel when you stand on Earth is not a force pulling you down. It is the same phenomenon as acceleration. And if free fall, which is supposedly falling under the full influence of gravity, feels like no force at all, then the person in free fall is not being acted on by a force. They are simply moving naturally, without interference, through whatever medium they happen to be in. This was the revolutionary inversion. Newton said gravity is a force that pulls objects toward each other. Objects in freefall are being pulled. They are under the influence of a force. The apple falls because the Earth's mass exerts a gravitational pull on it. The moon orbits because the Earth's gravity holds it. Everything is being pulled by everything else, constantly, universally, through the mysterious instantaneous action at a distance that Newton himself found philosophically absurd. But Einstein looked at the same situation and saw the opposite. The person in freefall feels no force. They are not being pulled. They are doing the most natural thing possible. They are moving freely through space, following the path that requires no push, no pull, no engine, no effort. The person in freefall is the one experiencing true natural motion. It is the person standing on the ground who is being interfered with. The floor of the room is pushing up against their feet, preventing them from following the natural path. The sensation of weight you feel right now is not gravity pulling you down. It is the ground pushing you up, accelerating you away from the path you would naturally follow if the floor suddenly disappeared. This turns everything upside down. Gravity is not a force that acts on you. The ground is a force that acts on you. Gravity is the natural state. Gravity is what happens when nothing interferes. And if gravity is the natural state of motion, if objects in freefall are simply moving freely without any force, then the question changes completely. The question is no longer what force is pulling these objects together. The question is, why does natural, unforced motion curve? Why does a freely falling apple accelerate toward the Earth? Why does the moon, following its natural path with no engine and no push, travel in a circle around the Earth rather than in a straight line? If no force is acting on the moon, why does its path bend? This is where Einstein needed a new framework. And to build it, he had to rethink the very nature of space and time. In our everyday experience, space and time seem like completely separate things. Space is where things exist. Time is when things happen. You move through space freely, going up, down, left, right, forward, backward. But time seems different. Time flows in one direction only, from past to future, and you cannot stop it or reverse it. Space is something you navigate. Time is something that happens to you. They feel fundamentally different. But in 1905, Einstein had already shown in his theory of special relativity that space and time are not separate at all. They are woven together into a single four-dimensional structure. You live in 3 dimensions of space and 1 dimension of time, and these 4 dimensions are connected. Moving through space affects how you experience time. If you move very fast, time slows down for you relative to someone standing still. This is not a metaphor. It is not a trick of perception. It has been measured directly with atomic clocks on high-speed aircraft and satellites. Time genuinely passes at different rates depending on how you move through space. Space and time are entangled, interwoven aspects of a single underlying reality. But Einstein's special relativity, published in 1905, dealt only with objects moving at constant velocities in the absence of gravity. It described how space and time behave for observers in uniform motion. It said nothing about acceleration and nothing about gravity. It was the equivalence principle that forced Einstein to extend his thinking from special relativity into something far more radical. Consider another thought experiment. You are standing inside a sealed elevator in a gravitational field, and you shine a beam of light horizontally from one wall toward the opposite wall. The light travels in a straight line and hits the far wall directly across from where it started. Now consider the same experiment from the outside, but instead of a gravitational field, the elevator is being accelerated upward by a rocket. As the light crosses the elevator moves upward. By the time the light reaches the far wall, the wall has moved upward slightly. From inside the elevator, the light appears to curve downward, following a bent path from one wall to the other. The acceleration causes the light path to bend. But the equivalence principle says gravitational acceleration and rocket acceleration are identical. No experiment can distinguish them. If light bends in an accelerating elevator, it must also bend in a gravitational field. Gravity must bend light. This was a stunning conclusion, and it emerged purely from the logic of the equivalence principle before Einstein had written a single field equation. Now, push the thought experiment one step further. Light has a frequency, and frequency is related to time. A light wave is an oscillation, and the rate of that oscillation is a clock. If you shine a beam of light upward inside a gravitational field, the light is climbing out of the gravitational well. The equivalence principle, applied carefully, shows that the frequency of the light must decrease as it climbs. It loses energy. Its oscillations slow down. A clock at the bottom of the gravitational field ticks more slowly than an identical clock at the top, because the light connecting them shifts frequency as it travels between them. Gravity does not just curve space. Gravity curves time. Clocks in stronger gravitational fields run slower, not because anything is wrong with the clocks, but because time itself passes at a different rate in curved space-time. Einstein realized this before he had the mathematical machinery to describe it precisely. The equivalence principle alone, without any field equations, without any tensor calculus, without any of the advanced geometry he would spend the next 8 years learning, told him that gravity must affect the flow of time. This was perhaps the most astonishing conceptual leap in the entire development of general relativity. A simple observation about the equivalence of gravity and acceleration led, through pure logic, to the conclusion that time is not uniform across the universe. Time runs at different speeds depending on the curvature of space-time, which depends on the distribution of mass and energy. The geometry of the universe determines not just where things go, but when things happen. Einstein's former mathematics professor, Hermann Minkowski, formalized this in 1908. He showed that the correct way to think about the universe is not as 3 dimensions of space with time running alongside, but as a single 4-dimensional continuum he called space-time. Every event, everything that happens anywhere in the universe, occupies a specific location in this 4-dimensional space-time. Not just a position in space, but a position in space and time together. Your life is not a series of moments happening at a fixed point. It is a path, a curve, a trajectory through 4-dimensional space-time. You are always moving through space-time. Even when you are sitting perfectly still in space, you are still moving through time. You're always traveling through space-time in one way or another. Now, in flat space-time, with no mass and no energy present, objects that are not being pushed or pulled travel in straight lines. This is just Newton's first law extended into 4 dimensions. An object with no force on it moves in a straight line through space-time at a constant velocity. If you throw a ball in empty space far from any gravitational source, it travels in a straight line forever. Its path through space-time is straight. This is the natural motion of a free object. But Einstein proposed something extraordinary. He proposed that mass and energy warp the geometry of space-time itself. A massive object like the Sun does not reach out and pull on the Earth through some invisible force. Instead, the Sun's mass curves the space-time around it. The presence of mass bends the fabric of space and time, distorting the geometry of the universe in its vicinity. And objects moving through this curved geometry follow the straightest possible paths available to them. Paths called geodesics, pronounced geodesics. These paths are the four-dimensional equivalent of straight lines. But in curved space-time, the straightest possible path is not what we would call straight in everyday experience. It is curved. It bends. It can loop around and come back to where it started. This is what an orbit is. The Earth is not being pulled toward the Sun by a force. The Earth is following the straightest possible path through the curved space-time created by the Sun's mass. It is doing the most natural thing an object can do in curved geometry. It is moving freely with no force acting on it, along a geodesic. And that geodesic happens to be an ellipse around the Sun, because the Sun's mass has curved space-time into a shape where elliptical paths are the straightest lines available. Consider an analogy. Imagine two people standing on the equator of the Earth, separated by some distance, and both start walking due north. They are walking in perfectly straight lines. Neither one turns left or right. Neither one deviates from their path. They walk as straight as they possibly can. And yet, as they approach the North Pole, they converge. They get closer and closer together. Eventually, at the pole, they meet. If they did not know the Earth was round, they might conclude that some invisible force was pulling them together. But no force is acting. They are both walking in perfectly straight lines. The reason they converge is that the surface they are walking on is curved. On a curved surface, straight lines that start out parallel can converge. The geometry itself causes the convergence, not any force, but the analogy of two people walking on a curved surface only captures part of the story. On a curved surface, parallel paths can converge. That gives you attraction, the appearance of a force pulling things together. But curvature does something more than attract. It produces tidal forces, the stretching and squeezing that reveal how gravity actually varies from point to point. And tidal forces are not a side effect of curvature. They are curvature. They are the physical, measurable manifestation of space-time geometry. Think about what happens when you fall toward a massive body like the Earth. Your feet are closer to the center of the Earth than your head. In curved space-time, the geodesic your feet are following converges slightly faster toward the center than the geodesic your head is following. Your feet are being pulled downward slightly more strongly than your head. The result is that you are being stretched vertically, pulled apart along the direction of fall. At the same time, because all geodesics near a spherical mass converge toward the center, the sides of your body are being pushed inward, squeezed horizontally. You are simultaneously stretched in one direction and compressed in the others. This is the tidal effect, and it is a direct, unavoidable consequence of the way geodesics converge and diverge in curved space-time. Near the surface of the Earth, these tidal forces are negligible. The difference in curvature between your head and your feet is so small that you cannot feel it. But near a black hole, where space-time curvature is extreme, tidal forces become catastrophic. An astronaut falling toward a stellar mass black hole would be stretched lengthwise and compressed sideways with such violence that physicists have given the process a darkly humorous name: spaghettification. The tidal forces would literally pull a human body apart long before it reached the event horizon, stretching it into a thin strand of matter drawn inward by the divergence of geodesics in violently curved space-time. Even in our everyday solar system, tidal forces have dramatic visible consequences. The ocean tides on Earth are a tidal effect. The moon's gravity pulls more strongly on the side of Earth closest to it and less strongly on the far side. This difference, this gradient in the gravitational field, stretches the Earth slightly along the line connecting it to the moon, creating two bulges of water on opposite sides of the planet. It is not simply that the moon pulls the ocean toward it. The moon's gravity varies across the diameter of the Earth, and that variation, that difference in curvature from one side to the other, creates the tides. The tides are not caused by a force, they are caused by a gradient in space-time curvature. They are geometry made visible in the rise and fall of the sea. This is what makes general relativity so different from Newton's description. In Newton's framework, gravity is a single force pulling two objects together. In Einstein's framework, gravity is a field of curvature, varying from point to point, producing not just attraction but stretching, squeezing, and distortion. The full richness of gravitational phenomena, from ocean tides to the spaghettification of matter near black holes, emerges from the geometry of space-time itself. This is precisely what Einstein proposed gravity does in 4 dimensions. Mass curves space-time. Objects moving freely through that curved space-time follow geodesics, the straightest possible paths, and those paths converge in the presence of mass, which is what we perceive as gravitational attraction. There is no force, there is only geometry. Gravity is not something that happens in space-time. Gravity is the shape of space-time. This explains something that had puzzled physicists since Galileo. Why does gravity accelerate all objects at the same rate regardless of mass? In Newton's framework, this was a strange coincidence requiring 2 different types of mass, gravitational mass and inertial mass, to be exactly equal for reasons no one could explain. But in Einstein's framework, there is no mystery at all. Gravity does not accelerate objects. There is no gravitational force doing the accelerating. Objects in freefall are simply following the geometry of space-time, and that geometry is the same for every object, no matter how heavy or light. A feather and a hammer follow the same geodesic, because the geodesic is a property of space-time, not a property of the object moving through it. The path is determined by the shape of the universe, not by the nature of the traveler. Galileo's observation that all objects fall at the same rate is not a coincidence. It is a direct and inevitable consequence of gravity being geometry. Now, Einstein's challenge was to express all of this mathematically. He needed equations that would describe precisely how mass and energy curve space-time, and how curved space-time determines the motion of objects. This was not easy. It took him nearly 8 years of intense effort, from 1907 to 1915, struggling with advanced mathematics that he had not learned as a student. He needed the tools of differential geometry, specifically a branch called Riemannian geometry, developed in the 19th century by the mathematician Bernhard Riemann. This geometry describes the properties of curved spaces of any number of dimensions. It was exactly what Einstein needed, but he had to learn it from scratch, often with the help of his friend and mathematician Marcel Grossmann. The struggle was genuine and prolonged. Einstein made wrong turns, published incorrect versions of the equations, spent months pursuing approaches that led nowhere, and occasionally despaired that the mathematics was beyond his ability. He later described the years between 1912 and 1915 as some of the most difficult of his life. He was racing against time in more ways than one. By 1915, the great mathematician David Hilbert was also working on gravitational field equations using similar mathematical tools, and Einstein was aware that Hilbert might arrive at the correct result first. In November of 1915, Einstein presented the final form of his field equations to the Prussian Academy of Sciences. The equations are among the most beautiful and powerful in all of physics, and they say something remarkably simple when stated in words. One side of the equation describes the curvature of space-time, how space and time are bent and warped at every point. The other side describes the distribution of mass and energy at every point, how much matter and energy is present, and how it is moving. The equation says these two things are equal. Mass and energy tell spacetime how to curve. The curvature of spacetime tells mass and energy how to move. This is general relativity, stated in a single sentence, but the simplicity of the statement conceals staggering mathematical complexity. The field equations are not one equation. They are a set of 10 coupled, non-linear, partial differential equations. They are among the most difficult equations in all of mathematics to solve. Each equation depends on the solutions of the others. The curvature of space-time depends on the distribution of matter, but the distribution of matter depends on the curvature of space-time, because matter moves along geodesics determined by the curvature, which is itself determined by the matter. Everything depends on everything else. The equations feed back into themselves. Finding exact solutions requires extraordinary ingenuity, and for most realistic physical situations, exact solutions are impossible. Physicists must rely on approximations and numerical computation. And yet, the very first thing Einstein did with his completed equations was solve a problem that had tormented astronomers for over half a century. He applied his field equations to the orbit of Mercury, calculating how a planet would move through the curved spacetime created by the sun's mass. And the answer came out perfectly. The 43 arcseconds per century of anomalous precession that Newton's equations could not explain emerged naturally from Einstein's mathematics. There was no fudging, no adjustment, no free parameters to tune. The field equations, applied to the sun's mass and Mercury's orbit, predicted exactly 43 arcseconds of additional precession per century. The number that had defied explanation for decades, the number that had sent astronomers on a futile search for a phantom planet called Vulcan, fell out of Einstein's geometry as an inevitable consequence of space-time curvature near a massive body. Einstein later told colleagues that when he saw this result, he was beside himself with excitement. His heart palpitated. Something had given way inside him. He wrote to his friend the physicist Arnold Sommerfeld that the Mercury result gave him great satisfaction. The equations worked. The universe was not governed by an invisible force pulling masses through space. The universe was governed by geometry. Space-time curved, and Mercury followed the curve. But Mercury was only the beginning. What makes the field equations so extraordinary is not just that they fixed an old problem. It is that they predicted entirely new phenomena that no one had imagined before. If mass curves space-time, then light, which also travels through space-time, should follow curved paths near massive objects. A beam of light passing close to the sun should bend, deflected by the curvature of space-time around the sun's mass. Newton's theory also predicted a slight bending of light. If you treated light as tiny particles with a small effective mass, but Einstein's prediction was exactly twice as large as Newton's. The two theories made different, testable predictions. The universe would reveal which one was right. Einstein's equations also formalized what the equivalence principle had already hinted at. Gravity affects time. The field equations gave this insight precise mathematical form, predicting exactly how much slower a clock should tick at the surface of the Earth compared to one high above it, or how much slower time should flow near a massive star compared to the empty space far from it. The differences are unimaginably small for everyday purposes, but the equations predicted specific numerical values that could be tested. And as we will see, they have been tested with extraordinary precision. The equations also predicted something even stranger. If massive objects curve space-time, then violent events involving massive objects, things like two stars orbiting each other at high speed, should create ripples in the fabric of space-time itself. These ripples would propagate outward at the speed of light, like waves spreading across the surface of a pond when a stone is thrown in. Einstein called them gravitational waves. They would stretch and compress space as they passed, alternately elongating distances in one direction and squeezing them in another. The distortions would be fantastically small, but they would be real. Physical waves in the structure of space and time, carrying energy and information outward from their source. Each of these predictions flowed directly from the field equations. Einstein did not add them by hand. He did not construct his theory to produce them. They emerged as unavoidable mathematical consequences of the single idea that mass and energy curve space-time, and that objects follow geodesics through that curvature. The theory had a life of its own. It made predictions Einstein had not anticipated. Predictions about the bending of light, the slowing of time, the existence of gravitational waves, and it made them with complete mathematical precision, specifying exact numerical values that could be compared to observation. In 1915, none of these predictions had been tested. The theory was pure mathematics, derived from a physical principle, the equivalence principle, and expressed in the language of Riemannian geometry. It was elegant. It was self-consistent. It resolved the Mercury problem that Newton could not. But science does not run on elegance. Science runs on evidence. Predictions must be tested against the real universe. A beautiful theory that fails an observational test is still wrong, no matter how beautiful it is. Einstein knew this. He knew his theory would stand or fall on whether its predictions matched what astronomers actually observed. The bending of light near the sun was the most accessible test. It could be measured during a total solar eclipse, when the sun's blinding disk is blocked by the moon and stars near the sun's edge become visible. By comparing the apparent positions of those stars during the eclipse to their known positions when the sun is elsewhere in the sky, astronomers could measure how much the sun's gravity deflected starlight. Einstein's equations predicted a deflection of 1.75 arcseconds for a light ray just grazing the sun's edge. Newton's framework predicted exactly half that value, 0.875 arcseconds. The difference was small, but measurable with the telescopes available in the early 20th century. The test would come, and its result would transform Einstein from an obscure theoretical physicist into the most famous scientist in the world. But the eclipse observation is only the beginning of a story of experimental confirmation that stretches across more than a century and extends to phenomena Einstein himself could not have imagined observing. His equations predicted things so exotic, so far beyond the technology of his era, that it would take 50 years, 70 years, a full 100 years before some of them could be tested. And every single one of those tests, without exception, confirmed what the geometry of space-time had predicted. That extraordinary record of confirmation, a record unmatched by any other theory in the history of science, is where we turn next. Because before we can understand how Einstein's equations break, we need to appreciate just how spectacularly, how relentlessly, how stubbornly they succeed. The first real test came in 1919, 4 years after Einstein published his field equations. The prediction was specific. Starlight passing close to the sun should be deflected by the curvature of spacetime, bending the apparent position of the star outward by 1.75 arcseconds for a ray just grazing the solar edge. Newton's framework, treating light as tiny particles influenced by gravity, predicted roughly half that value. The two theories disagreed by a factor of 2, which meant a careful measurement during a total solar eclipse could distinguish between them. During an eclipse, the moon blocks the sun's blinding disk, and for a few precious minutes, stars near the sun become visible. By photographing those stars and comparing their positions to where they appear when the sun is elsewhere in the sky, astronomers could measure whether the sun's mass had shifted the starlight and by how much. The British astronomer Royal Frank Dyson organised 2 expeditions to observe the total solar eclipse of May 29, 1919, recruiting the physicist Arthur Eddington to lead one of them. One team travelled to the town of Sobral in northern Brazil. The other, led by Eddington himself, travelled to the island of Principe off the west coast of Africa. The logistics were formidable. This was 1919. The First World War had ended barely 6 months earlier. International scientific collaboration was strained. Equipment had to be shipped across oceans, assembled in remote locations, calibrated under unfamiliar conditions, and operated during a fleeting window of totality lasting only a few minutes. Cloud cover could ruin everything. A single bad exposure could waste years of preparation. Both teams managed to take photographs. The Sobral team obtained clearer images, while Eddington's plates from Principe were partially obscured by clouds. But after months of careful measurement and analysis, the results were announced on November 6, 1919, at a joint meeting of the Royal Society and the Royal Astronomical Society in London. Dyson, who had championed the test from the beginning, presented the findings. The measured deflection of starlight matched Einstein's prediction, not Newton's. Light bent by the amount general relativity demanded, roughly 1.75 arcseconds, twice what Newton's framework predicted. The impact was immediate and dramatic. Newspapers around the world published the story. The Times of London ran a headline declaring that scientific concepts of the fabric of the universe would have to be changed. Einstein, who had been known primarily within the physics community, became an international celebrity overnight. A theoretical prediction derived from pure mathematics about the curvature of four-dimensional space-time had been confirmed by observation. The universe bent light exactly as Einstein's geometry demanded. In the century since Eddington's expedition, gravitational lensing has become one of the most powerful tools in astronomy. We now observe it routinely, not just from our sun, but from galaxies, galaxy clusters, and other massive objects across the cosmos. When light from a distant galaxy passes near a massive foreground galaxy cluster on its way to Earth, the cluster's gravity bends and distorts the light, stretching the distant galaxy's image into arcs and rings. In some cases, the lensing effect produces multiple images of the same background object, each image arriving by a slightly different curved path through space-time. These lensing observations allow astronomers to map the distribution of mass in the universe, including dark matter, which does not emit light but still curves space-time. Every single lensing observation ever made is consistent with general relativity. The theory predicts not just that light bends, but by exactly how much, depending on the mass of the lensing object and the geometry of the light path. And every measurement confirms the prediction. But gravitational lensing was only the first confirmation. Einstein's equations also predict that gravity affects time itself. If space-time is curved near a massive object, and time is one dimension of that curved fabric, then time should flow at different rates, depending on how deep you are in a gravitational field. A clock closer to a massive body, deeper in the gravitational well where space-time is more sharply curved, should tick more slowly than an identical clock farther away, in flatter space-time. This is gravitational time dilation, and it is not a subtle philosophical point. It is a measurable, physical effect. The first direct laboratory test came in 1959. Robert Pound and Glenn Rebka, working at Harvard University, set up an experiment in a tower only about 22.5 meters tall. They used gamma rays emitted by radioactive iron at the bottom of the tower and measured their frequency at the top. General relativity predicted that the gamma rays would be very slightly blue shifted, gaining a tiny amount of energy as they climbed upward through the Earth's gravitational field, because time runs faster at the top of the tower than at the bottom. The predicted shift was absurdly small, roughly 2 parts in 1,000 trillion. But the Pound-Rebka experiment, using a technique called the Mossbauer effect to achieve extraordinary frequency precision, detected the shift. It matched Einstein's prediction to within 10%, and later refinements brought the agreement to within 1%. Time genuinely runs at different speeds at the top and bottom of a 22-meter tower on Earth. The difference is fantastically small, but it is real and measurable. In 1971, physicists Joseph Haffel A. and Richard Keating performed an even more dramatic test. They loaded highly precise cesium atomic clocks onto commercial airliners and flew them around the world, once eastward and once westward. General relativity predicted that the flying clocks would disagree with identical clocks left on the ground at the United States Naval Observatory because of 2 effects. First, gravitational time dilation. The clocks at altitude were farther from the Earth's center, in slightly weaker gravity, in slightly flatter space-time, so they should tick faster than the ground clocks. Second, the motion of the aircraft introduced time dilation from special relativity, which slows clocks that are moving relative to a stationary observer. The 2 effects worked in the same direction for the westward flight and partially cancelled for the eastward flight, producing different predicted offsets for each trip. When Haffel A. and Keating compared the flying clocks to the ground clocks, the measured time differences matched general relativity's predictions within the experimental uncertainty. Clocks that had flown around the world at altitude returned, showing different elapsed times than clocks that had stayed on the ground. Time itself had passed at different rates, depending on altitude and speed. This was not a theoretical calculation. It was a measurement, performed with real clocks on real aircraft, and the results confirmed Einstein. But the most dramatic daily demonstration of gravitational time dilation is something billions of people rely on without thinking about it: the Global Positioning System, GPS. The system works by triangulating signals from a constellation of at least 24 satellites orbiting the Earth at an altitude of roughly 20,200 kilometers. Each satellite carries an extremely precise atomic clock and broadcasts its time and position. Your GPS receiver picks up signals from multiple satellites, compares their arrival times, calculates the distances based on the speed of light, and determines your position on the Earth's surface. Here is where general relativity becomes essential. The satellites are orbiting at 20,200 kilometers above the Earth's surface. At that altitude, they are in a weaker gravitational field than clocks on the ground. Space-time is flatter up there. General relativity predicts that the satellite clocks should run faster than ground clocks by about 45 microseconds per day. Special relativity predicts an opposing effect because the satellites are moving at about 3.9 kilometers per second relative to the ground, which slows their clocks by about 7 microseconds per day. The net result is that the satellite clocks gain roughly 38 microseconds per day relative to ground clocks. 38 microseconds sounds negligible. It is 38 millionths of a second. But light travels about 11.4 kilometers in 38 microseconds. Without correcting for relativistic time dilation, GPS position errors would accumulate at a rate of roughly 10 kilometers per day. Within a single morning, your GPS would place you in the wrong neighborhood. By afternoon, it would place you in the wrong city. Within a week, it would be off by an entire country. The GPS system compensates for this by adjusting the satellite clock frequencies before launch, pre-correcting them so that their tick rate matches ground clocks when viewed from the Earth's surface. This correction is derived directly from Einstein's field equations. Every time you use GPS to navigate, to find a restaurant, to track a delivery, to guide an aircraft to a runway, you are relying on general relativity being correct. If Einstein were wrong, GPS would not function. It would drift into uselessness within hours. The fact that billions of GPS receivers around the world give accurate positions every second of every day is a continuous, real-time, global-scale confirmation that space-time curves exactly as Einstein described. General relativity also predicts a phenomenon called frame dragging. If space-time is a flexible, deformable fabric, then a massive rotating object should drag space-time around with it as it spins, twisting the fabric in the direction of rotation. Imagine a bowling ball spinning on the surface of a trampoline. The ball does not just dent the trampoline, it also drags the surrounding fabric slightly in the direction of its spin, twisting the surface around it. Similarly, the rotating Earth should twist the space-time around it, dragging it very slightly in the direction of Earth's rotation. This twisting is extremely faint, far smaller than the simple curvature caused by the Earth's mass, but general relativity predicts it with mathematical precision, and it should be measurable with sensitive enough instruments. In 2004, NASA launched Gravity Probe B, a satellite carrying 4 ultra-precise gyroscopes made from nearly perfect quartz spheres, the most spherical objects ever manufactured. The gyroscopes were set spinning and pointed at a distant guide star. In flat space-time, with no frame dragging, the gyroscopes should remain pointing at that star indefinitely. But if the Earth's rotation drags space-time around with it, the gyroscope axes should slowly precess, drifting away from the guide star by a tiny but calculable amount. The predicted drift from frame dragging was about 39 milliarc seconds per year, an almost unimaginably small angular shift. The experiment ran for over a year, and after extensive data analysis, the results, presented by lead scientist Francis Everett and published in 2011, measured the frame dragging effect to within 19% of general relativity's prediction. Independent measurements using satellite laser ranging have since confirmed the effect through entirely different methods. Spacetime is dragged by rotating mass. The Lenser-Tearing effect is real. The fabric of the universe twists when mass spins. Now we arrive at what many physicists considered the most spectacular confirmation of general relativity in its entire history: gravitational waves. Einstein predicted them in 1916, just 1 year after completing the field equations. If massive objects curve spacetime, then massive objects that accelerate violently should create ripples in spacetime that propagate outward at the speed of light, like waves spreading across the surface of a pond. These gravitational waves would carry energy away from the source, stretching and compressing space as they pass through. But Einstein himself doubted whether gravitational waves were real physical phenomena or merely mathematical artifacts of his equations. The predicted distortions of space were so fantastically small that he considered them practically undetectable. For decades, physicists debated whether gravitational waves carried real energy and whether they could ever be observed. The first indirect evidence came in 1974, when Russell Hulse and Joseph Taylor discovered a pair of neutron stars orbiting each other at tremendous speed, a system now known as the Hulse-Taylor binary pulsar. One of the neutron stars is a pulsar, emitting regular radio pulses like a cosmic lighthouse. By timing these pulses with extraordinary precision over years and eventually decades, astronomers measured the orbital period of the two neutron stars and found it was decreasing. The two stars were spiraling closer together, losing orbital energy. The rate of energy loss matched exactly, to within a fraction of a percent, the rate predicted by general relativity for energy carried away by gravitational waves. The two neutron stars were radiating gravitational waves as they orbited, and those waves were draining energy from the system, causing the orbit to slowly shrink. Hulse and Taylor received the Nobel Prize in Physics in 1993 for this discovery. It was powerful indirect evidence that gravitational waves exist and carry energy exactly as Einstein's equations predict. But the direct detection of gravitational waves required an entirely new kind of instrument, one sensitive enough to measure distortions of space itself. The laser interferometer. Gravitational wave observatory known as LIGO was designed for exactly this purpose. LIGO consists of two enormous detectors, one in Livingston, Louisiana, and one in Hanford, Washington, separated by about 3,000 kilometers. Each detector is an L-shaped instrument with two arms, each arm 4 kilometers long. A laser beam is split and sent down both arms simultaneously. The beams bounce off mirrors at the far ends and return, recombining at the junction. When no gravitational wave is passing, the two beams arrive back in perfect sync and cancel each other out through a process called destructive interference. But when a gravitational wave passes through, it stretches one arm and compresses the other by a tiny amount, changing the relative lengths. This causes the returning laser beams to arrive slightly out of sync, producing a detectable signal. The sensitivity required is almost beyond comprehension. LIGO must detect changes in the length of its 4-kilometer arms, smaller than 1/10,000th the diameter of a proton. That is a measurement precision on the order of 10 to the negative 19 meters. To achieve this, LIGO's mirrors must be isolated from every conceivable source of vibration, seismic activity, traffic, ocean waves, even the thermal motion of atoms in the mirror surfaces. The engineering is extraordinary, pushing the absolute limits of what human technology can accomplish. On September 14th, 2015, both LIGO detectors simultaneously registered a signal. The signal was a characteristic chirp, a rising frequency and amplitude lasting a fraction of a second, matching exactly the pattern predicted by general relativity for the final moments of two black holes spiraling into each other and merging. The event, designated GW150914 after its detection date, involved two black holes roughly 36 and 29 times the mass of the Sun, located about 1.3 billion light-years from Earth. In the last fraction of a second before they merged, the two black holes were orbiting each other at nearly half the speed of light, completing dozens of orbits per second. The energy released in gravitational waves during the final merger was staggering. Roughly 3 solar masses worth of energy was converted entirely into gravitational radiation in less than a second. For that brief instant, the merger radiated more power than all the stars in the observable universe combined. The detected signal matched the prediction from general relativity with remarkable precision. The waveform, the shape of the signal as it changed over time, followed Einstein's equations so closely that physicists could extract the masses, spins, and distance of the two black holes directly from the signal. The announcement was made in February of 2016, and it sent shockwaves through the scientific community. Rainer Weiss, Kip Thorne, and Barry Barish received the Nobel Prize in Physics in 2017 for the detection. Gravitational waves were real. Space-time ripples exactly as Einstein predicted. We had opened an entirely new window on the universe, detecting it not through light of any kind, but through the vibrations of space-time itself. Since that first detection, LIGO and its European counterpart Virgo have detected dozens of gravitational wave events, including mergers of neutron stars, mergers of black holes with neutron stars, and black hole binaries of various masses. Every single detection is consistent with general relativity. The waveforms match. The predicted relationships between mass, spin, distance, and signal strength hold. Not a single observation has contradicted the theory. Gravitational wave astronomy has gone from a single historic detection to a thriving field producing regular observations, and general relativity has passed every test without a single anomaly. And then came the image. In April of 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole shadow. Not an artist's illustration, not a computer simulation. An actual image constructed from radio wave observations taken by a network of telescopes spanning the entire globe, from Hawaii to Spain to the South Pole, linked together to form a virtual telescope the size of the Earth. The target was the supermassive black hole at the center of the galaxy M87, a monster with a mass of roughly 6.5 billion times the mass of the Sun. The image showed a bright ring of superheated gas surrounding a dark central region, the shadow of the black hole itself. The shadow exists because light that crosses too close to the black hole is captured by the curvature of space-time, bent inward past the event horizon, the boundary beyond which nothing can escape. Light just outside this boundary is bent into orbits around the black hole. creating the bright ring, while the interior remains dark because no light emerges from within. The size and shape of the shadow match the prediction of general relativity to within the measurement precision. Einstein's field equations, applied to a rotating black hole of that mass, predicted a shadow of a specific angular size when viewed from Earth, about 55 million light-years away. The observed shadow was consistent with that prediction. In 2022, the Event Horizon Telescope released an image of the black hole at the center of our own galaxy, Sagittarius A star. This black hole is smaller, about 4 million times the mass of the Sun, and much closer, about 26,000 light-years away. Its shadow also matched general relativity's predictions. Consider what we've established. Einstein's field equations, published in 1915, predicted the bending of light by gravity, confirmed in 1919 and observed routinely ever since. They predicted gravitational time dilation, confirmed in laboratories, on aircraft, and embedded in the daily operation of GPS. They predicted frame dragging by rotating masses, confirmed by Gravity Probe B. They predicted gravitational waves, ripples in the fabric of space-time itself, confirmed by LIGO and observed dozens of times with waveforms matching the theory's predictions. They predicted the existence of black holes, objects whose gravity curves space-time so severely that nothing can escape, producing shadows of specific sizes and shapes, confirmed by direct imaging with the Event Horizon Telescope. This is not a theory that passed one test. This is a theory that has passed every test. Every prediction general relativity has ever made has been confirmed by observation. No experiment in over a century has found a deviation. The measurements have grown more precise with every decade. From Eddington's photographs with margins of 20%, to LIGO's waveforms matching theory, to fractions of a percent, to atomic clock measurements confirming gravitational time dilation to parts per million, with precision tests of the equivalence principle reaching parts in 1,000 trillion. The more precisely we test general relativity, the more precisely it is confirmed, across an enormous range of conditions from the surface of the Earth, to binary pulsars to colliding black holes, 1 billion light-years away. And this is what makes the next part of our story so deeply unsettling. Because despite this extraordinary, unbroken, century-long record of success, despite predictions confirmed to 14 decimal places, despite being woven into the technology billions of people use every day, general relativity contains within its own mathematics a clear and unavoidable signal that the theory is incomplete. The equations that have never failed a single observational test also predict conditions under which they produce nonsensical answers. Not vague answers, not approximate answers, infinities, numbers that blow up without limit, that have no physical meaning, that cannot correspond to anything real. The most successful theory ever constructed predicts its own failure. And it does so not in some exotic hypothetical scenario, but in places we know exist. At the centers of black holes, at the first instant of the Big Bang, at the precise locations where gravity is strongest, where general relativity should reign supreme, the equations tear themselves apart. That breakdown, and what it reveals about the deepest unresolved problem in all of physics, is where we go next. In 1915, only weeks after Einstein published his completed field equations, a German physicist named Carl Schwarzschild found the first exact solution. Schwarzschild was serving on the Russian front during the First World War when he worked out the mathematics, and he sent the result to Einstein by letter from the trenches. The solution described the curvature of spacetime around a perfectly spherical, non-rotating mass. It was elegant, exact, and immediately useful. It gave precise predictions for how planets orbit stars and how light bends near massive bodies. But hidden inside the mathematics was something deeply strange. The Schwarzschild solution contained two troubling features. At a specific radius from the center of the mass, a boundary now called the Schwarzschild radius, or event horizon, certain terms in the equations appeared to blow up to infinity. And at the very center, at a distance of 0 from the mass, the curvature of spacetime became genuinely infinite. At first, most physicists assumed both infinities were artifacts of the particular coordinates Schwarzschild had used, not real physical features of spacetime. And for the event horizon, they turned out to be right. Later work showed that the infinity at the Schwarzschild radius is a coordinate illusion. An observer falling through the event horizon would experience nothing special at that exact boundary. The spacetime there is perfectly smooth, but the infinity at the center is different. No change of coordinates removes it. It is a genuine physical singularity, a point where curvature diverges without limit, and the mathematics of general relativity produces meaningless values. Einstein himself was skeptical that any physical process could compress matter into the tiny volume needed to form such an object. For decades, the prevailing attitude was that nature would somehow prevent the formation of what we now call a black hole. Some pressure, some force, some mechanism would halt the collapse before matter reached that critical density. But beginning in the late 1920s and accelerating through the 1930s, theoretical work by Subramanian Chandrasekhar and others showed that stars above a certain mass have no known force capable of stopping their gravitational collapse once their nuclear fuel is exhausted. When a massive star exhausts its nuclear fuel, the core collapses. For the most massive stars, no known physics can halt this collapse. Not the pressure of electrons squeezed together, not the pressure of neutrons packed into the densest state of matter we understand. Nothing stops it. The equations of general relativity predict the matter continues falling inward without limit, compressing to infinite density at a single dimensionless point. This point is the singularity, and it is not optional. In the 1960s, Roger Penrose and Stephen Hawking proved a series of mathematical theorems demonstrating that singularities are not special cases or unusual solutions. They are generic. Under very broad and physically reasonable conditions, general relativity predicts the formation of singularities whenever enough mass is concentrated in a small enough region. You do not need exotic matter or unusual configurations. You need only gravity, sufficient mass, and general relativity. The singularity theorems showed that the formation of infinities is not a bug in the equations. It is a feature. It is what the theory predicts, inevitably and unavoidably, under conditions that exist in the real universe. This matters because we know black holes exist. We have imaged their shadows. We have detected the gravitational waves produced when they collide. We have observed stars orbiting Sagittarius A star, the supermassive black hole at the center of our galaxy, and measured their trajectories with enough precision to determine the black hole's mass at roughly 4 million times the mass of the Sun. We are not talking about hypothetical objects. We are talking about real, observed structures in the universe that general relativity describes with extraordinary accuracy on the outside, at the event horizon and beyond, where predictions match observations to remarkable precision. But at the center, where the theory should be most powerful, where curvature is most extreme and gravity is strongest, the mathematics gives an answer of infinity. Infinity is not a physical quantity. You cannot have infinite density. You cannot have infinite curvature. These are not things that exist in the real world. When a physical theory produces an infinity, it is not describing reality. It is telling you that the theory has been pushed beyond its domain of validity. It is telling you that the mathematical framework you are using, however successful it has been in other contexts, does not apply here. The infinity is a signal, a warning light, an admission written into the equations themselves that something is missing. And the singularity at the center of a black hole is not the only place this happens. General relativity produces the same kind of infinity when you trace the expansion of the universe backward in time. The universe is expanding. Galaxies are moving apart from each other. Space itself is stretching. If you reverse this expansion, running the clock backward, the universe gets smaller and denser and hotter. Keep going, and everything in the observable universe, all the matter and energy contained in trillions of galaxies, compresses into a smaller and smaller volume. General relativity predicts that if you trace this backward far enough, you reach a moment of infinite density, infinite temperature, and infinite curvature. This is the initial singularity, the Big Bang singularity, the moment at which the universe apparently began. But just as with black holes, the infinity is not a physical description. It is the theory breaking down. It's a general relativity confessing that it cannot describe the first instant of the universe, the moment when conditions were most extreme, when gravity was strongest, when a complete theory of gravity matters most. The theory that describes the large-scale evolution of the universe with stunning precision that predicts the cosmic microwave background radiation, the abundances of light elements forged in the first minutes after the Big Bang, the formation and distribution of galaxies across billions of light years. This same theory produces nonsense at the very beginning of the story it tells so well everywhere else. So we have two situations where general relativity fails. The centers of black holes and the initial instant of the universe. In both cases, the failure takes the same form. The equations produce infinities, meaningless quantities at precisely the points where gravity is most extreme. This is not a coincidence, it is a pattern, and it points to a single underlying problem. General relativity is a classical theory. It describes space-time as a smooth, continuous fabric that bends and warps in response to mass and energy. At every point, space-time has a definite curvature, a definite geometry. You can measure distances, calculate angles, trace geodesics. Everything is smooth, precise, and well-defined. There are no jumps, no gaps, no fuzziness. The geometry of space-time in general relativity is as sharp and exact as the geometry of a polished sphere. But the other great pillar of modern physics tells a completely different story about reality at very small scales. Quantum mechanics, the theory that governs atoms, subatomic particles, and the fundamental forces of nature, describes a world that is not smooth at all. In quantum mechanics, energy comes in discrete packets called quanta. Particles do not have definite positions and definite momenta at the same time. The act of measurement affects what is measured. Physical quantities that seem continuous at large scales turn out to be granular and discontinuous at small scales. The quantum world is fuzzy, probabilistic, inherently uncertain. Things do not have precise values until they are observed, and even then, the outcome is governed by probability rather than certainty. For most of physics, this tension between smooth classical gravity and fuzzy quantum mechanics does not matter. Gravity operates on large scales, planets, stars, galaxies. Quantum mechanics operates on small scales, atoms, electrons, photons. Their domains rarely overlap. You do not need quantum mechanics to calculate the orbit of Mars, and you do not need general relativity to describe the behavior of an electron in an atom. The two theories govern different regimes, and in their respective regimes, both are spectacularly successful. You can use them side by side without conflict, as long as you do not try to apply both simultaneously to the same situation. But there is a scale at which the two theories must both apply. It is called the Planck scale, named after the physicist Max Planck, who introduced the fundamental constant that bears his name. The Planck scale is defined by combining three fundamental constants of nature: the speed of light, the gravitational constant, and Planck's constant, into units of length, time, and mass. The Planck length is approximately 1.6 times 10 to the negative 35 meters. The Planck time is approximately 5.4 times 10 to the negative 44 seconds. These are unimaginably tiny. The Planck length is roughly 20 orders of magnitude smaller than a proton. If you enlarged a Planck length to the size of a grain of sand, a single proton would span roughly 3 light years, nearly the distance to the nearest star beyond our Sun. At the Planck scale, the smooth spacetime of general relativity and the fuzzy uncertainty of quantum mechanics collide head-on. The reason is fundamental and unavoidable. In quantum mechanics, the Heisenberg uncertainty principle tells you that the more precisely you know the position of something, the less precisely you can know its momentum, and vice versa. To probe very small distances, you need very high energy probes with very short wavelengths. But energy curves space-time. Einstein showed that mass and energy are equivalent. Concentrate enough energy in a small enough region, and you create such intense curvature that you form a black hole. At the Planck scale, the energy required to probe that distance is so enormous that the act of measurement itself creates a black hole larger than the distance you are trying to measure. You cannot probe smaller. The measurement destroys the thing you are trying to measure. Space and time as continuous, well-defined concepts cease to have meaning. This is not just a practical limitation that better technology could overcome. It is a fundamental boundary built into the structure of physics itself. General relativity describes space-time as a smooth continuum. Quantum mechanics demands that at sufficiently small scales, everything must exhibit quantum behavior, uncertainty, discreteness, fluctuations. At the Planck scale, these two demands are mutually exclusive. You cannot have both a smooth, continuous space-time and quantum uncertainty at the same scale. The frameworks are mathematically incompatible. Physicists have tried to resolve this incompatibility using the techniques that work brilliantly for the other fundamental forces. The electromagnetic force, the weak nuclear force, and the strong nuclear force have all been successfully described by quantum field theories. In these theories, forces are mediated by particles. The electromagnetic force is carried by photons. The weak force is carried by W and Z bosons. The strong force is carried by gluons. Each of these theories was initially plagued by infinities. When you calculated the probability of a particle interaction, the answer came out as infinity, which is obviously wrong. But physicists developed a technique called renormalization. that tames these infinities. You absorb the infinite quantities into the definitions of physical constants like mass and charge, and the remaining calculations give finite, meaningful, and extraordinarily precise answers. Quantum electrodynamics, the quantum field theory of the electromagnetic force, has been tested to better than 10 decimal places. It is one of the most precisely confirmed theories in all of science. But when you try to apply the same approach to gravity, it fails catastrophically. If gravity is mediated by a particle, the hypothetical graviton, then you should be able to write a quantum field theory of gravity and renormalize its infinities the same way you renormalize those in quantum electrodynamics or quantum chromodynamics. But you cannot. Gravity is non-renormalizable. When you calculate particle interactions involving gravitons, you get infinities. When you try to absorb those infinities into redefined constants, new infinities appear. When you try to absorb those, still more infinities appear. The process never terminates. Every step generates new divergences that cannot be removed. The mathematical machinery that works flawlessly for the other three forces produces an infinite cascade of meaningless results when applied to gravity. This is the deepest form of the incompatibility between general relativity and quantum mechanics. It is not that we have not tried hard enough. It is not that we need more computing power or cleverer mathematics. The standard methods of quantum field theory, the methods that have been the most successful theoretical framework in the history of physics, fundamentally do not work for gravity. The reason is rooted in the nature of gravity itself. In general relativity, gravity is not a force acting within space-time. Gravity is the curvature of space-time. The other forces operate on a fixed background stage. Particles interact within space-time, but gravity is the stage. Trying to quantize gravity using the tools designed for forces that act on a fixed stage is like trying to quantize the stage itself while the actors are still performing on it. Everything becomes tangled. The background you are trying to define is the same thing you are trying to quantize. The mathematics collapses under its own circularity, and this matters. This is not an abstract mathematical complaint. Without a quantum theory of gravity, there are physical questions we simply cannot answer. What replaces the singularity at the center of a black hole? General relativity says the curvature becomes infinite. Quantum mechanics says infinities do not occur in nature because quantum effects should intervene at the Planck scale, preventing true infinities from forming. But we do not have a theory that combines the two. Is the singularity replaced by a region of extreme but finite curvature? Does space-time itself dissolve into something more fundamental? Some pre-geometric quantum structure that has no analog in our current theories? We cannot calculate the answer, because the only theory that describes gravity accurately breaks down precisely where we need it most, and the only theory that handles quantum effects cannot incorporate gravity. What happened at the very first instant of the Big Bang? General relativity says everything began from a singularity of infinite density and temperature. But that infinity is the theory failing, not describing reality. Quantum effects must have been dominant at the Planck scale conditions of the early universe. But without a quantum theory of gravity, we cannot describe those first moments. We cannot say whether time itself had a beginning, or whether the Big Bang was a transition from a previous state. We cannot say whether the initial conditions of the universe were determined by some deeper principle, or were simply arbitrary. The first fraction of a second of cosmic history, the moment that set the stage for everything that followed, for the formation of atoms and stars and galaxies and planets and life, remains hidden behind a wall of mathematical incompatibility. There is another consequence of this incompatibility that sharpens the conflict into what many physicists consider a genuine paradox rather than merely an unsolved problem. It involves black holes, and it strikes at the very foundations of quantum mechanics itself. In 1974, Stephen Hawking showed that black holes are not perfectly black. Quantum effects near the event horizon cause black holes to emit a faint glow of thermal radiation, now called Hawking radiation. The mechanism arises from the interaction between quantum field theory and the curved spacetime of the event horizon. Pairs of virtual particles constantly fluctuate into existence throughout space, normally annihilating each other almost immediately. But near the event horizon, one particle in a pair can fall inward past the boundary while the other escapes outward as real radiation. The escaping radiation carries energy away from the black hole, and over immense timescales, the black hole gradually loses mass and shrinks. Given enough time, an extraordinarily long time for any black hole of astronomical size, the black hole evaporates entirely and disappears. This creates a profound problem. Quantum mechanics has a fundamental rule, one of the deepest principles in all of physics. Information cannot be destroyed. The quantum state of a system at any moment contains, in principle, complete information about its past and future. You can scramble information. You can spread it out. You can make it extraordinarily difficult to recover. But you cannot erase it from the universe. This principle is called unitarity, and it is essential to the mathematical consistency of quantum mechanics. Without it, probabilities do not add up to 1. The framework collapses. But a black hole appears to violate unitarity. Objects that fall into a black hole carry information with them. Information about their quantum states, their composition, their history. That information crosses the event horizon and, according to general relativity, reaches the singularity where it is destroyed by infinite curvature. Meanwhile, Hawking radiation is thermal. It is random. It carries no information about what fell in. It is the same regardless of whether the black hole swallowed a star, a planet, or a library containing the complete works of every civilization that ever existed. When the black hole finally evaporates, all the information that fell in appears to be gone, erased from the universe. Quantum mechanics says this is impossible. General relativity says the singularity destroys everything. The two theories give flatly contradictory answers. This is the black hole information paradox, and it has consumed theoretical physics for half a century. Some physicists believe the information somehow escapes during evaporation, encoded in subtle correlations in the Hawking radiation that are invisible without a complete quantum gravity theory to decode them. Others have proposed that the information is stored on the event horizon itself, encoded on a two-dimensional surface like a hologram, a concept called the holographic principle. Still, others suspect the singularity does not actually destroy information because the singularity does not actually exist. That a quantum theory of gravity would replace the singularity with a region of extreme but finite curvature through which information could survive. But none of these proposals can be confirmed without a working theory of quantum gravity. The paradox remains open, and its very existence is a direct consequence of the incompatibility between the smooth spacetime of general relativity and the fundamental principles of quantum mechanics. It is not an abstract tension between two mathematical frameworks. It is a concrete physical contradiction about what happens to real information in real black holes. Does spacetime itself have a fundamental structure at the Planck scale? Is it continuous and smooth all the way down, as general relativity assumes? Or is it quantized, made of discrete units, as quantum mechanics might suggest? Are space and time fundamental aspects of reality, or do they emerge from something deeper, something pre-geometric and purely quantum mechanical? These are not philosophical questions. They are physics questions with definite answers that we cannot currently obtain, because the necessary theory does not yet exist. And here we must be very careful about what this means and what it does not mean. General relativity is not wrong. That word implies the theory makes incorrect predictions, and it does not. We established a moment ago just how relentlessly general relativity has been confirmed, from tabletop experiments to colliding black holes a billion light years away. That record is essential context for what comes next, because despite that unbroken century of success, the theory contains within its own mathematics a clear and unavoidable signal that it is incomplete. When people say general relativity breaks down at singularities, they do not mean the theory is flawed in the way that Aristotle's physics was flawed, producing incorrect predictions across its entire domain. They mean that general relativity has a domain, and singularities lie outside it. The theory is extraordinarily, spectacularly correct within its domain. It just does not cover everything. This is a familiar pattern in physics. Newton's theory of gravity was not wrong either. It gives correct predictions for an enormous range of situations. Spacecraft trajectories, bridge engineering, planetary orbits, all of these are calculated using Newtonian gravity, and they work. Newton's theory fails only in extreme conditions, near the speed of light, in very strong gravitational fields, where space-time curvature is significant. In those conditions, you need general relativity, but general relativity does not replace Newton. It contains Newton as a limiting case. When gravity is weak and speeds are low, Einstein's equations reduce exactly to Newton's equations. Newton is not wrong. Newton is approximate, correct within a specific domain, but incomplete beyond it. General relativity expanded that domain enormously, but it did not eliminate Newton's mathematics. It absorbed it. The expectation, the hope, the working assumption of most physicists is that whatever theory eventually resolves the incompatibility between general relativity and quantum mechanics will do the same thing. It will not replace Einstein. It will contain Einstein as a limiting case. When gravity is not too strong and distances are not too small, when you are safely outside the Planck scale, the new theory will reduce exactly to general relativity, just as general relativity reduces to Newton under the right conditions. The new theory will explain everything general relativity explains, match every prediction, reproduce every confirmed result, and then go further. It will describe the Planck scale. It will resolve singularities. It will provide finite, meaningful answers where general relativity produces infinities. It will tell us what happens at the center of a black hole and what happened at the very beginning of the universe. But we do not have that theory. There are candidates. String theory proposes that the fundamental constituents of nature are not point particles, but tiny vibrating strings at the Planck scale, and that gravity emerges naturally from the vibrations of these strings. Loop quantum gravity proposes that spacetime itself is quantized, made of discrete units woven together like a fabric at the Planck scale, with area and volume taking only specific discrete values. Other approaches exist: causal set theory, asymptotic safety, emergent gravity, each with its own mathematical framework, its own philosophical commitments, its own strengths and weaknesses. But none of these candidates has been confirmed by experiment. None has made a prediction that has been tested and verified. The reason is simple and sobering. The Planck scale is so extraordinarily far below any distance we can probe with current technology that direct experimental tests of quantum gravity seem almost impossibly out of reach. The Large Hadron Collider, the most powerful particle accelerator ever built, probes distances of roughly 10 to the negative 19 meters. The Planck length is 10 to the negative 35 meters. The gap between what we can measure and what we need to measure is 16 orders of magnitude, a factor of 10,000 trillion. We would need a particle accelerator vastly larger than our entire solar system to directly probe the Planck scale with current technology. This does not mean the problem is hopeless. Indirect approaches exist. Observations of the cosmic microwave background radiation might carry imprints of Planck-scale physics from the earliest moments of the universe. Gravitational wave observations from the most extreme events, colliding black holes, neutron star mergers, might reveal tiny deviations from general relativity that point toward the correct quantum gravity theory. Ultra-precise laboratory experiments testing gravity at very small distances might detect modifications predicted by specific theories. The search for quantum gravity is active, intense, and ongoing, pursued by thousands of physicists around the world using every tool available. But as of today, the problem remains unsolved, and it has been unsolved since the 1930s, when physicists first recognized the incompatibility between quantum mechanics and general relativity. For nearly a century, some of the most brilliant minds in physics have worked on this problem, and no one has cracked it. This is not like most problems in science, where progress is steady and solutions emerge after sufficient effort. This problem may require a conceptual breakthrough as profound as Einstein's own, a fundamental rethinking of what space and time actually are. A shift in perspective so radical that we cannot yet imagine what it looks like from the other side. And so we arrive at the full answer to the question we set out to explore. What gravity actually is, according to the best theory we have, is the curvature of space-time caused by mass and energy. It is not a force pulling objects through space. It is the shape of space and time themselves, warped by the presence of matter, guiding the paths of everything that moves through the universe. Objects in free fall feel no force because no force is acting on them. They are following the natural geometry of the cosmos, moving along geodesics through curved space-time. This description, Einstein's description, has been tested more precisely and confirmed more thoroughly than any other theory in the history of science. It predicts the bending of light, the slowing of time, the rippling of space-time, the shadows of black holes. It has never failed a single observational test. And why does this answer still break physics? Because the same equations that describe all of this with such breathtaking accuracy also predict their own limits. They predict singularities, conditions of infinite curvature and infinite density at the centers of black holes and at the origin of the universe. They are incompatible with quantum mechanics at the Planck scale, the scale where both gravity and quantum effects must matter simultaneously. The most successful theory of gravity ever conceived cannot describe gravity in the most extreme conditions gravity creates. The equations contain, within their own beautiful and precise mathematics, the clear signal that something beyond general relativity must exist. Not because the theory is wrong, but because reality in its most extreme forms demands a deeper description. We do not know what that deeper description looks like. We do not know whether space-time is truly continuous or secretly granular at the Planck scale. We do not know whether the singularity at the center of a black hole is a real feature of the universe or an artifact of using a theory beyond its domain. We do not know what happened at the very first instant of cosmic history, when the entire observable universe was smaller than a proton and the conditions were so extreme that both gravity and quantum mechanics must have been operating simultaneously. These are the deepest open questions in all of physics. Questions that touch the foundation of what space and time and matter actually are at the most fundamental level. What we know is this: gravity, the most familiar experience in all of human life, the force you have felt every moment since you were born, the phenomenon so ordinary that you rarely think about it, is actually the curvature of the four-dimensional fabric of space and time. And the theory that reveals this truth, a theory of such extraordinary beauty and predictive power that it has withstood a century of increasingly precise testing without a single failure, also tells us, in its own mathematical language, that it is not the final word. Something deeper is waiting, something that resolves the infinities, that reconciles the smoothness of space-time with the graininess of the quantum world, that describes gravity all the way down to the smallest scales of existence. We do not have it yet, but the search for it is the search for the most fundamental truth about the universe we inhabit. It is the search for what lies beneath everything, beneath space, beneath time, beneath the geometry that governs the cosmos. What would a successful theory of quantum gravity actually give us? Not just the resolution of singularities, though that alone would be revolutionary. It would answer questions that we cannot even properly formulate with our current tools. Consider the nature of space-time itself. Is the smooth four-dimensional fabric of general relativity truly fundamental, woven into the deepest layer of reality? Or is it emergent, arising from something more primitive, the way temperature arises from the motion of molecules? You cannot find temperature in a single molecule. Temperature is a collective property that only appears when billions of molecules interact. Some approaches to quantum gravity suggest space-time might be similar. At the Planck scale, there might be no space and no time at all, only a network of quantum relationships, entanglements between fundamental degrees of freedom that, when viewed from a distance, when coarse-grained over trillions upon trillions of Planck-scale elements, produce the smooth, four-dimensional space-time that general relativity describes so well. If this is true, then space and time are not the stage on which physics plays out. They are part of the performance, emerging from something deeper and more abstract. Consider the beginning of the universe. General relativity says the Big Bang was a singularity, a point of infinite density where time began. But if space-time is emergent, then the question of what happened before the Big Bang changes character entirely. There may not have been a before in the temporal sense, but there may have been a prior state in some more fundamental framework, a quantum gravitational configuration from which space-time itself condensed. Some approaches suggest the Big Bang was not a beginning at all, but a transition. A quantum bounce from a collapsing previous phase, with the singularity replaced by a moment of extreme but finite Planck scale density. If true, Our universe did not emerge from nothing. It emerged from a previous state whose nature only a theory of quantum gravity can describe. Consider the relationship between gravity and information. In recent decades, theoretical physicists have uncovered deep and unexpected connections between the geometry of spacetime and the structure of quantum information. The entanglement between quantum systems appears to be related to the connectivity of spacetime itself. More entanglement between two regions corresponds to those regions being closer together in the emergent geometry. Less entanglement corresponds to greater distance. Removing all entanglement between two regions might sever the spacetime connection between them entirely. If these connections are real, then spacetime is not just described by quantum mechanics. Spacetime is built from quantum mechanics, constructed from patterns of entanglement and information at the most fundamental level. Gravity, the curvature of spacetime, would then be a manifestation of how quantum information is organized across the universe. These are not idle speculations. They are active research programs pursued by thousands of physicists worldwide. They represent humanity's attempt to answer the most fundamental question science has ever asked. Not what the universe contains, but what the universe is made of at the very bottom. Not what happens in space and time, but what space and time themselves are. The answer, when it comes, will not diminish Einstein. It will complete what he started. It will extend the geometric understanding of gravity past the barriers his own equations identified, into the regime where the smooth fabric of space-time dissolves, and something deeper, something we do not yet have words for, takes over. And it is, without question, the deepest and most important unfinished story in all of science.